Okay, so let's go ahead and talk a little bit more about these atomic orbitals and all of the notation that goes along with atomic orbitals. And then that'll lead us into electron configurations, which we're kind of getting there. We're sort of in it a little bit. I've been mixing and matching a lot of this stuff. So let's do a quick little review of this quantum theory. So essentially what we're saying is that you can think of the electron as being a wave. Now, in fact, sometimes it behaves like a particle, sometimes it behaves like a wave. It's actually, in a sense, there's nothing, there is, at the atomic level, the distinction between a wave and a particle, it breaks down. There's actually something which means that it's both. Something can be a wave and it can be a particle at the atomic level or at the subatomic level. Okay, so it's a wave, which means it has a wavelength. Talking about its wavelength is somewhat useful, but really what we end up doing is running it through the mathematics. And when you run it through the mathematics, so you put it through a physical model, and you do calculations with it. And what the results are this. You get these quantum numbers that describe it. So the first one is n. Can go all as high as you want. And this essentially gives you the energy of the electron, just like Bohr said. And then you get this L, which can be 0, 1, 2, 3, all the way up to n minus 1. And this gives you the shape of what we call an orbital. Okay, so that's the space around the nucleus that this wave is occupying. Then you get this third quantum number, which is called m sub L, which has to do with magnetic properties. And it can be 0, but it can also be negative. So it can be plus or minus 1, plus or minus 2, all the way up to plus or minus L. And this gives you the direction of the orbital. Okay, so if you combine those three quantum numbers, you get these certain shapes, you get these orbitals. So we talked about how the nucleus is at the center, and you get an orbital that looks like a sphere, like a ball. And it's vibrating. It's this vibration around the nucleus. That's where the electron is. The electron is, in a sense, the electron is the vibration, right? So it's vibrating itself. It's occupying that space. And then you can have larger ones that have larger values of n. So these vibrations are bigger and bigger and bigger. There's some details about them that I'm not going to go over. Okay, not very good drawings there. Okay, so this is the case where n equals 1, 2, 3, 4. So as you can see, the orbitals get larger as n increases, and the larger they are, the more energy they have. Okay. And then what happens is you can start looking at other types of vibrations. So for example, you might have one that looks something like this. Okay. Or even bigger, right? Just like with these orbitals here, the top ones, this shape, the orbitals can get bigger as well. Okay, so something like that, right? And again, this is n equals 1, 2, I'm sorry, 2. This one only can happen if n is equal to 2 or more. You can't have this if n is equal to 1. N equals 3, and then n equals 4. So let me put n equals for all these. Okay. And again, there's other shapes as well. There's the ones with 4 lobes, and there's the one with 6 lobes, and we have names to those. So what's the difference between these ones that are spherical and these ones that have lobes? So we have names for them, but we also have a quantum number for them. So up here, this is the case where L equals 0. So if L is equal to 0, you get one of these shapes here, a sphere. if L is equal to 1, then you get this shape here. Okay? So what that's telling you is that this second quantum number here is giving you the shape, right? Let me make a little box over here so you can see the third one. Remember we said if n is equal to 3, you can have this one where you have 4 lobes, right? And that's the case where L is equal to 2, okay? And again, you know, if n is equal to 4, then it just gets even bigger. Just like with the other ones, they get bigger. But still L is equal to 2, right? So the L is telling you the shape. So this shape is L equals 1, this shape is L equals 2, this shape is L equals 0. The N tells you how large it is, how much energy it has. Further, you know, the bigger it is, the more energy it has. And then there's this M sub L, which tells you what direction it's pointing in. So the idea of M sub L is that it might be pointing in this direction, or it might be pointing in this direction, or it might be pointing out of the, you know, into and out of the plane of this drawing that I'm doing here. And so you can give values to this. For example, this might be -1, this one might be 0, and this would be +1. So there's your M sub L equals 0, comma, plus or minus 1, right? And so then there's certain patterns for this. But the thing about the shapes is that just, you know, giving out the quantum numbers is annoying, right? Oh, that's M sub L is -1, or that's L equals 0. It's more convenient to give names. And so we call this subshell notation. People have different names for it, but you can call it subshell notation. And so subshell, what you do is you write the first quantum number, n, and then you write a letter for L. So this is telling you what n is, and then this is telling you what L is. And you just have to remember S, P, D, F for L is 0, 1, 2, 3. So if you see 1s, what that's telling you is n equals 1 and L equals 0. If you see 4f, that tells you that n equals 4. And then where's f right here? L is equal to 3. Okay? And so, you know, you have these quantum numbers, and sometimes it's useful to use notations because these subshells have different energies. So the lowest energy is called the 1s. You know, the smaller n is, the less energy it has. The smaller L is, the less energy it has. So as those numbers go up, the energy goes up. So 1s, this is, you know, n equals 0 and L equals 0. I'm sorry, n equals 1 and L is equal to 0. That's about as low as you can get. It is as low as you can get. You can't have any lower than that because n can't be 0. So that's the lowest one. That subshell is called 1s. And then the next one is 2s. N equals 2, and L is equal to 0 again. The general rule is that at the higher n is, the higher energy is, but you can also take n plus L. Okay, so for example, here, n plus L is equal to 1 plus 0, which is 1. Here it's 2 plus 0. So it's 2. So you see how that's higher? N plus L is higher. It's 2. So that's going to be higher in energy. So what's the next one? The next one is 2p. So what does that equal? N plus L is 2 plus 1, which is 3, right? Okay. And then the next one is 3s. So here n plus L is 3, right? Because it's 3 plus 0. So you get a tie there, right? These two are a tie. So which one goes higher? If it's a tie, the one that goes higher is the one with the higher n, okay? The one with the lower n goes down lower energy. And then you just keep on going, you know? And so 3s and then 3p. and then 4s, and then 3d comes into play, and then 4p comes into play, and you just keep on going. 5s, 4d, 5p, and you can keep on going. You don't have to go much further than that though, okay? So those are called subshell designations or subshell symbols. So 1s, 2s, 2p. Notice that for the p's you have 3 orbitals, and for the d's you have 5. For the f's you would have 7. And again, the reason for that is that the orientations are m sub l. So if you have only one possible orientation, you only have 1 orbital. But if you have 3 possible orientations, you're going to have 3 orbitals. And if you have 5 different orientations, you're going to have 5 orbitals. So what happens with the d's is that m sub l has 5 possible values. 0 plus or minus 1 plus or minus 2, that's 5. So you get 5 orbitals. So now each orbital is represented with a line on this energy level diagram, okay? Each orbital. So how many orbitals are in the 1s subshell? Just one. There's just 1 orbital. In the 2s subshell, just 1 orbital. In the 2p, now you got 3. In the 3s, you got 1. In the 3p, you got 3, and so forth and so on. So we have lots of orbitals. So in theory, an atom has a nucleus, and then it has all these possible locations or regions of space that the electrons can occupy. So that kind of leads us into the next topic, which is how does this work in terms of multi-electron atoms? Like how do we, where do the electrons go if you have 20 electrons? Which of these orbitals do they go into? And there's some very straightforward rules about that that we'll look at, okay? So before I do that though, I want to show you how confusing this can be, because if you think about it, when we talk about the electron initially, when we do this in chemistry, what we do is we have a nucleus and then we think of a little ball, right? There's a little ball going around the nucleus. So that's your electron, is that little ball. But then we said when we do redox chemistry, we're going to represent the electron as a charged particle with a symbol, right? E negative, that's the electron. So we use that for redox chemistry. Now what we're going to, then we said, look, you know, the electron's actually a wave, right? So then we said it's this vibration, that was de Broglie, around the nucleus, right? So it's a vibration around the nucleus. So that was a wave. So we represented it like this. For this topic now, the way we're going to represent the electron is by using an arrow that's pointing upward or downward. Okay. Upward or downward. And if it's pointing upward, this is called spin up. And if it's pointing downward, this is called spin down. Okay. And the reason that we need this is because it turns out the electron is an interesting little particle. It's a fermion. And the electron has a 4th quantum number. And this is called the spin quantum number, and it's a magnetic property. And the values of m sub s can be positive or negative, but it's a half. So it's got very kind of weird properties. We don't need to go into the details of the meaning of that. It's not even fully understood anyways. Okay, so it has 2 possible values. And so the way we do this is we say that if it's spin up, it's plus a half. And if it's spin down, it's minus a half. So see, we have another way of representing the electron now with arrows. And that can be confusing, but that's just sort of the nature of how we've learned about the structure of the universe. We use this when we're doing redox. This is sort of the theoretical idea of it being a wave, but it's going to be very useful for us to use this notation right here, the spin up, spin down with the arrows. That's very useful. And here's why. There's something called the Pauli exclusion principle. Okay, I guess you could call it PEP if you want to. I've never seen it done that way, but Pauli exclusion principle. It's a fascinating idea. If you were to take two atoms, so let's just use a simple model of an atom. So you have two atoms. And you bring them close to each other, right? It turns out once they get close enough to each other, they will repel each other. They will push each other away. And the force of repulsion becomes very, very large. Okay. Now, the reason for that, when they get really, really close, sometimes people think it's because of the electrons. They're negatively charged, so they repel each other. But it's actually perhaps more having to do with this idea of the Pauli exclusion principle, which is this. Two electrons in the same atom can never have the same four values of N, L, M sub L, and M sub S. They can never have the same four values in the same atom. Okay, it's impossible. And the Pauli exclusion principle is something that's just observed. It's not, there's no real, we don't have a reason for why it exists, but it seems to be a very powerful relationship. So what that means is that if you have an atom with more than one electron, those electrons have to have at least one different value of their quantum numbers. So let me show you what I mean by that, just by using the simplest of these energy level diagrams. So let's say we have an atom. Here's 2s. Here's 2p. Okay, I'm just going to do the first few. And let's say that we've got, let's start with one electron. Okay, if you have one electron, it's going to go into the lowest energy orbital first. Okay, that's the ground state, right? So that's the lowest energy. And notice I put it spin up. And the reason I put it spin up is that we just tend to do that. We have an agreement among us that if there's only one electron in an orbital, we just draw it spin up, okay? So I've drawn it spin up. So there's your one electron, perfectly fine. Now, what I'm going to do for that one electron is I'm going to write out its quantum numbers. It's in n equals 1, so that's 1 for n. It's in an s orbital, so that's 0 for L. M sub L is 0 plus or minus 1 plus or minus 2, but it can never be more than L or less than negative L. So if L is 0, M sub L also has to be 0. So we know that one. And now, again, I said I'm going to put it spin up, so it's plus a half. And those are the four quantum numbers for that one. Now, suppose we put a second electron in the same atom. Okay, look at all these orbitals. It looks like there's plenty of room for other electrons, and there are. The question is, where does it go? Well, in general, if you think about rocks, if you roll rocks down a hill, where do they go? They go to the bottom of the hill first. So there's a tendency for the electrons to want to go into this lowest energy orbital first until it's full, and then they go to higher ones. Okay, so let's take this second electron. What happens if I try to put it in the lowest possible orbital? That would be the 1s. Well, I'm just going to do that. And I'll do it dash just so that we can see that I'm just kind of experimenting. I'll put it in there too. Okay. I also made it spin up. So now let's go through the quantum numbers for that electron. It's in a 1s, so that's 1, 0. If L is 0, M sub L's got to be 0. And it's plus 1/2, no problem, right? But there is a problem because of the Pauli exclusion principle. In this atom, these two electrons now have exactly the same four values of the quantum numbers. And the Pauli exclusion principle says that's impossible. So this would never happen. That structure is just unstable. So something would happen. In fact, you probably can't even force the electron in there. So there's something wrong with that. So I've got to erase it. So what, and I'm going to erase this over here. So what's another possibility? We have two things. One is we want to get it in as far as we can, closest to the nucleus, which is the 1s orbital. But we also don't want to disobey this Pauli exclusion principle. So here's one way it could work. Suppose I take that second electron and I put it spin down. Okay. Well, if I do that, it's still in a 1s, so that's 1, 0. M sub L is 0 because L is 0. But now it's 1 minus 1/2, right? Spin down is minus 1/2. That works. It gets it into the lowest possible energy, and it doesn't violate the Pauli exclusion principle because one of those 4 quantum numbers is different. Okay? And that's what happens in nature. When you have 2 electrons, there is a tendency, even though they are negatively charged and in theory should repel each other, right? There is a tendency for them to spread out into the same space as a pair of electrons, 2 electrons, even though they have the same negative charge. And that's because even though they repel each other from their negative charge, it's a lot of energy to get up to the 2s. So it's actually lower in energy to have them in the same orbital, but opposite spins. And this ends up being a quantum phenomenon that we never would have thought of with the planetary or the nuclear model of the atom, or even the Bohr theory, right? We are now claiming that electrons have a tendency to form pairs in the same region with opposite spins. That's the catch. They have to have opposite spins. So if they're in the same orbital, they can't be in both spin up. That's impossible. If they are both spin down, that can't happen either. That's impossible. They've got to be opposite spins. And that ends up being important in terms of chemical bonding, superconductors, all kinds of aspects of nature involving the electron, which is, you know, what we're made of, right? So this idea that they form pairs is actually intrinsic of how we're built. Our atoms bond with each other due to this tendency for electrons to form pairs. It's not that they're attracted to each other. It's that if they're in the same region and have opposite spins, that results in the lowest energy possible. Okay? Now, that's the Pauli exclusion principle. And what this says is we can have a maximum of 2 electrons in one orbital. Okay? No more than 2. Can't have 3 because if you have a third one, it would have to be spin up or spin down. Now, if the universe were different and you could have m sub s is plus 1/2, plus 3/2, minus 1/2, and minus 3/2, and you had 4 possible values, then you could put 4 electrons into one orbital. But our universe, you can only have plus 1/2 or minus 1/2. That's up here. That's the limits of what we call fermions. And so that means we can't fit more than 2. Okay. Now, what if we put a third electron in? Well, we know it can't go into that first orbital, the 1s orbital. There's no room in there for it to go into the 1s. So the next possible orbital, is the 2s. So we're going to put it in the 2s. And again, when this is not actually a physical law that it has to be spin up. It's our notation. We put the first one in spin up, and then we put the second one in spin down. It's arbitrary which one we call up and down. There is up and there is down in nature, but it's arbitrary which one is which, right? In the same way that electrical charge is arbitrary. We could have called the electron positively charged and the proton negatively charged, but we chose to make the electron negative and the proton positive. Okay, so a third electron. So third electron. Only possibilities for, well, I couldn't say the only possibility, but the next reasonable possibility is that it goes into the 2s. And again, I'm going to write it spin up just to be consistent with our idea that the first one going in will be spin up. There's no real reason for that, but we just do it that way. Okay, so now n is 2. So it's 2. It's still an s, so L is 0. M sub L is still 0 because M sub L is plus or minus L. And now it's spin up, so it's plus 1/2. So that third electron doesn't have the same 4 quantum numbers as the first 2. There's a difference, right? N is different, and pretty much n is different, right? But only one quantum number needs to be different, okay? So what about a fourth electron? Well, just like with the 1s, there's room for one more in the 2s. So again, see this idea of pairing? The electrons are pairing up. They're going into the same orbital. And so that is going to be spin down. So your fourth electron is 2, 0, 0. If it's in the same orbital, the first 3 quantum numbers will be the same. And then it's got to have a different spin, so minus 1/2. Okay? Now, let's get to the fifth electron. Okay, the fifth electron, again, we can't put any more in the 2s. We can't put any more in the 1s. So the next available orbital is the 2p. So now we have a choice. We could put it in the left one, the middle one, or the right one. And in fact, it doesn't really matter. But again, our sort of agreement of how we do this is we put it on the left and go left to right. Now, I'm not sure if that's true everywhere. I can imagine countries where you might go right to left. I don't know, to be honest with you. But generally, the textbooks will tell you put it in the one on the left. Spin up, again, our sort of idea we're going to spin up. So now n equals 2, but now it's a p orbital, right? So that's 1. Remember, S, P, D, F, 0, 1, 2, 3. It's now we have a choice. And for M sub L. And this is completely arbitrary. And but we do, not completely, we do know the only possibilities are -1, 0, and +1. Those are the 3 possibilities, right? Because if L is 1, M sub L could be -1, 0, or +1. It could be any of those 3. So you can pick any one you want. You could put -1, you could put 0, you could put +1. I agree. We're still going to do spin up is the first one, so +1/2. So if you want, you could make this -1, or you could make it 0 here and +1. It doesn't really matter. But what we would say is that there's 3 possible values of M sub L, -1, 0, and +1. Okay. Now, what happens when we get to 6? Something interesting. There's an issue, a decision we have to make, which the electron essentially has to decide. And that is, do we put a second one in here? Or do we put a second one here? Or do we put a second one here spin down? Which one do we do? And there is actually an interesting observation about nature. And that is, if you have more than one orbital at the same energy level, right? These are all at the same energy level, these 3 here on the vertical axis. If they're at the same energy level, we call that degeneracy. This is where you have orbitals at the same energy level. If that happens, then what you do is you put the second one not in the same orbital as the first one, but into the second orbital. Okay, so that's just something you got to remember. If you have orbitals at the same level, same subshell, right? 2p is a subshell. You put the second one in the second orbital, same spin. And actually, this is something we can measure. It turns out there is interactions of the electrons, and they will actually be the same spin. So we'll put them both spin up. That's something that's actually true. They will be the same spin. Okay, so now here's what happens. You've got 2, 1, right? 2p, so it's 2, 1. And then again, it's arbitrary which one this is. Is it -1? Is it 0? Is it +1? It's one of them, right? And again, it's +1/2. Okay, now where's the difference? Remember, 2 electrons in the same atom can't have the same 4? Well, if this one's -1, then this one can't be -1, right? It's got to be 0 or +1. It's got to be one of the others. They can't be the same. Okay, so there's your second. Now, this tendency for them to spread out across the subshell, that's called Hund's rule. So let me write that down for you. So Hund's rule, this is for degenerate orbitals. Degenerate meaning the same energy, right? Orbitals at the same energy level, okay? What they tend to do is they tend to spread out one by one into separate orbitals because those orbitals are at the same energy. So what does this do in terms of spin? Right? The first one, m sub s is +1/2. The second one, it's also +1/2. The third one, it's also +1/2. And it turns out spin is additive. If one particle has a certain amount of spin and the other one has the same spin, you can add the spins. So you get a total spin. Spin 3 times 1/2, which is 3/2 plus 3/2. Okay, so that means that these 3 electrons will have the same spin and it will be an additive spin. Now, how does that play out physically? If electrons have this property called spin, as I said yesterday, spin is a magnetic property. It behaves, the atom behaves, or the electron behaves, as though it were a charged particle that's spinning, and it forms a magnetic field. And so these 3 electrons are spinning with the same value and the same sign, so it becomes an additive magnetic property. It becomes an additive magnetic property. So the atom itself will start to behave like a little magnet. And so now we have some interesting phenomena that we can describe because of this. We know that certain elements in nature are magnetic, right? Like iron is magnetic. You make magnets out of iron. There's these more complicated ceramic magnets. There's these rare earth magnets that you can buy pretty cheaply on Amazon now. What is giving rise to that magnetism? Well, it's not the whole story, but part of the story is the idea of this magnetic spin. That if you have unpaired electrons, see how they're unpaired? They're not in the same orbital. There's no opposite spin, right? So like these two down here, they cancel each other. One is spinning up, one is spinning down. So if you add the spin numbers, +1/2, -1/2, you get 0. So these electrons essentially cancel the magnetic properties. But these ones are spin up and there's nothing to cancel them. So overall, that particular atom will start to behave as though it has a magnetic moment and it has a magnetic property. So this now allows us to explain some of the phenomena that we observe in nature about magnetism. Normally in chemistry, we talk about the electrical properties of the electron and we just ignore the magnetic properties. This is a case where we don't do that. This is a case where we now have an explanation for why certain elements have magnetic properties. It's because of Hund's rule, that if you have more than one electron and they're in degenerate orbitals, they're going to have the same spin, not opposite spins. So overall, the atom will be a magnetic dipole, it'll have a magnetic moment. This ends up being important in things like MRI. You've heard of magnetic resonance imaging. MRI is an example where the spin of electrons and protons can be measured in such a way that you can actually do some clinical studies. Okay. All right, so that's Hund's rule. There's one other kind of term that people use regarding this idea that we're putting the electrons, let me just do it this way, from one orbital up to the next. So let me do it this way. 1s, 2s, 2p, 3s, 3p. The tendency of the electrons to fill in this direction, right? This is the filling order. Right, they go from this orbital to that one, and then these get filled, and then this gets filled, and then these get filled. That's called the Offbow principle. Offbow just means filling up. So it's the filling up principle. So they have a tendency to go from low energy orbitals. Once that orbital is filled, goes up to the next level. So up to higher energy orbitals. Okay. Now, a little bit more about the notation. Sometimes we use boxes or circles. So you might see the 1s orbital represented like with a little box, or you might see it represented with a little circle. I tend to just use a little horizontal line to represent it that way. But in any case, whichever notation you want to use, we represent the electrons as little arrows, spin up, spin down, spin up, spin down. Any of those three notations are perfectly fine. Textbooks often use this one. The older textbooks use this. Some of the more advanced textbooks use this one on the right. And then I think Alex actually uses a little square. It doesn't matter, but in any case, it's the same idea, okay? Now, let me show you the order of filling again. I know I did that yesterday, but I want to show you the order of filling. It goes 1s. Now I'm doing it horizontally instead of vertically, right? Because we tend to write horizontal in English. 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, okay? So all the way, 4f, 5, I know that's hard to see. Let me make that a little bit clearer. 4f, 5d, and then 6p. And then generally, you don't need to go further than that. I'm going to show you why you don't need to go further than that. Here's what happens. With any of the s orbitals, you only have one orbital, so that's 2 electrons. For the p, you've got 3 orbitals, so 1, 2, 3, 4, 5, 6 electrons, a maximum of 6. The d, you have 5 orbitals, and you can have 2, remember 2 electrons max per orbital. So here you have 2 electrons, 6 electrons, 10 electrons. And then what about the F? So your F orbitals have 7. So that means you can get up to 14 electrons. And so these numbers start getting really big. So here's what happens. Suppose I have a lot of electrons. Where are they going to go? Offbow principle. 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, so forth and so on, right? So let me write these orbitals, the maximum number of electrons you can get in them. S, you can get 2, right? S, you can get 2. P, you can get 6. D, you can get 10. So 2, 6, 2, 10, right? There's your first D right there, 3D. You can get up to 10 in there. The P, you can get up to 6. The S, 2. The D, 10. 6, 2, 14 now. You can go up to 14 electrons if you do all these F orbitals, right? And then we have 5D. I know it's hard to see that. 5D is 10. And then 6S is 6. That's a lot of electrons now, right? Let me count up how many electrons we have. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 66, 70, 80, 86 electrons right there. So that's a lot. Now, we do have elements that are more then 86, right? We have elements that go all the way up in theory up to 118, although in practice, 96, 98 is about the limit of what you find even in laboratories. In nature, it's 92 is the limit. So what happens after we do 6p? Well, after you get the 6p, the next one is the 7s. So that gets you another 2. So now you're up to 88. And then the next one would be the 5f. That can go up to 14. So that's 88 plus 14, 98, 100. Now you're up to 102. And then you can do your 6D. And that can go up to 10. So now you're up to 112. And then you can do your 7p, and that can go up to 6, and that gets you up to 118. So I went through the whole thing. That's the entire periodic table, up to every element that humans have produced or knowingly have produced in laboratories for elements that only last for microseconds or nanoseconds. They can make 10 of these atoms or something like that, right? So that's essentially everything. You're not going to need to worry about all of those. The only ones you really need to worry about, for the most part, are up to around 50 or 60. And that's going to be the ones that are around here. Okay. All right. So that's a lot. Offbow principle, building up, low energy to high energy. You got the Pauli exclusion principle, which means that you can have a maximum of 2 electrons in an orbital. So spin up, spin down. Remember, spins are additive. So if you have 2 electrons that are opposite spin, 0 magnetism, right? It's called diamagnetism. Then you get to this idea that once you get up to 2p or 3p or 3d or 4p or 4d or 5p, you have multiple orbitals, degenerate orbitals in a subshell. So those degenerate orbitals will now use Hund's rule, which is spin up, spin up, spin up, and then spin down, spin down, spin down, up to 6, okay? For the P's anyways. So let's take a look at some problems here. I did a lot of sort of background on that, but what really is helpful for people once we've done all this background is to start looking at some of the problems, okay? So this is now 6.8, and this is called electron configurations. Okay. All right, so the first one on Alex they ask you to do is they say draw a box diagram of the electron configuration. And they want you to do a neutral atom of argon. Argon is AR, just be careful. Arsenic is AS, argon is AR, okay? So here's your starting point. What you do is you look up the element in the periodic table. The number you want is the atomic number. Remember, the atomic number is not the number of electrons per se, it's the number of protons, right? So this tells you have 18 protons. But it says it's a neutral atom. So what does that mean? That means that the number of electrons is equal to the number of protons. So you got 18 electrons. That's all you need, okay? All right, that's the number, 18 electrons. That's the one you're gonna use. When we get into ions, we'll talk more about adding and subtracting electrons. They won't be neutral, but for neutral atoms, the number of electrons and protons are equal, okay? So how do we do this? It's a box diagram. So box diagram could be done vertically, it could be done horizontally. I'm gonna do it vertically. So remember, if you do it vertically, energy is increasing in the Y direction. Let me draw that again. I don't know why I crimped myself out over there. So energy. And then you just draw little boxes instead of lines. Okay, so here's your 1s. Here's your 2s. Here's your 2p. Here's your 3s, 3p. Now, I know what's going to happen, so I'm not going to go beyond 3p. Okay, I'll stop right there. Okay, so 18. So here's what you do. Maximum 2 electrons per orbital. Okay, pay attention to Hund's rule. Now, a maximum of 2 electrons per orbital, that's really the Pauli exclusion principle. And then you got the Offbow principle. Those are the 3 principles we use. The Offbow just says start at the lowest and go up to higher and higher. Maximum of 2 per orbital, but make sure if you're in degenerate orbitals, which is the same subshell, like a 2p or a 3p, make sure you do 1 electron across spin up. And also remember, the first electron should be spin up, second one should be spin down. So we got 18, so it's just counting. Just count away. 1, 2, right? See how I did that? Maximum of 2. 3, 4, maximum of 2. We stop there. That's 4. Now, 5, 6, 7. See, the reason I did that is Hund's rule. Degenerate orbital, same energy. You go 1, 1, 1 all the way across. Once you've got 1 in, then you go back again. That's the sort of trick. So now we're up to 10. So 5, 6, 7. If there were only 7 electrons, then we would have 3 spin up and no spin down in that subshell. But we have 10, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. We've now got 18. We're done. This is the electron configuration of argon. And what I want to point out is that if you look at the noble gases, starting with neon. So here's helium, and then you get neon, and then you get argon, and then you get krypton, and then you get xenon. And I'm not going to do radon because I don't think it's not going to fit in there, but radon's underneath it. Starting with neon, all of these down here, they all end in P6. So see how it ends in P6, 3p6? So the outermost electrons are going to have 6 electrons in the P subshell. Remember, each of these are subshells. And so there it is on a vertical. If you were going to do it horizontally looks a little different. Let me show you horizontally. You would just draw your box this way. 1s, 2s, 2p, 3s, and then 3p. And I'm going to put these 3 together just to say they're degenerate. They're the same energy. So this is increasing energy in this direction. And then again, spin up. Sometimes people will use half arrows like that because it's easier to draw. I actually like doing it that way. Okay, and there you go. So there's your argon. So this is the electron configuration of argon. Now remember, let's bring it back to this idea of these orbitals, right? So you've got this little orbital. So here's the nucleus. You got this little orbital. It's a 1s, right? 90% probability. There's your 1s. But you've got 2 electrons in there. So there's 2 electrons vibrating in that space. And then a little bit bigger than that, you got this 2s. So now there's another 2 electrons that are vibrating outside of those first 2, right? They're undergoing vibrations in here. So a bunch of vibrating particles, right? All these electrons are vibrating and they have spin, right? So they also have property. Then you got the 2p, right? So now you got these 2p orbitals, but there's 3 of them. So the 2p orbitals look like this. So remember, this is one orbital right here. This is a 2p. It has 2 lobes. So that's just one orbital. The second orbital is this one. And then the third one is right here. So there's 6 electrons, 2 in here, 2 in here, and 2 in there. They're all vibrating too. All these electrons are vibrating like waves, okay? Think about sound. Sound can have lots of frequencies, right? If you have an orchestra playing, you have all these different musical instruments vibrating in the same room. Same thing here. And then you get the 3s. What's the 3s? Well, the 3s is even bigger. 2 electrons in the 3s. And then you got the 3p. So what's the 3p look like? It's a bigger a bigger orbital than the 2p, but it has essentially the same shape, right? There's some differences I'm not going to go over. So your 3p looks something like this. Okay, so you have all those 18 electrons in there vibrating, doing their thing. Some of them are magnetic spin up. Some of them are magnetic spin down. They're all in that space doing the vibrations, okay? Generally, this is the picture we use, these diagrams. It's pretty complicated. This ends up being important if we start thinking about how atoms will bond to each other, because the orientations of these orbitals and their energy levels gets important. So sometimes we go back and forth. We go between this and we go back between this. But this is more common. We're going to use something like that notation. Okay. So let me show you another example. Carbon is easy. Let's not do carbon. Let's do nickel. So draw the electron configuration of nickel. Okay, now this one doesn't have us do a box diagram. And it does say it's a neutral atom. Okay, so when you're doing this, one way to do it is with the box diagram. Another way is with what we call, so I'm just looking at it. It looks like they actually just want you to do the box diagram. I'm not sure. Okay, so they didn't say box diagram here. It says draw, so I guess draw means the box diagram. But I'm going to, after I do the box diagram, I'm going to show you the notation, okay? So here's how we'll do nickel. So first of all, you look it up in the periodic table. Nickel is element number 28. And let's see, iron is 55, 57. I guess it's around 50, 58 point something. It's around 58 is the atomic mass, but we don't need the atomic mass. We just need the atomic number. Okay, now remember, that's the number of protons. So that means there's 28 protons, but it says it's a neutral atom. So that means it's 28 electrons also. Okay. So let's take a look. What do we do now? Same idea. The diagram is the same. It's just how many electrons you're going to put in there. Now this one's a little bit longer, so a little taller. Okay. Okay, so 1s. I guess I'll do it this way. Now these orbitals converge in energy, but if we draw it converging, it's really hard to draw them. So there's your 2p. So for that reason, I'll just show them equally spaced. They're not really equally spaced. See, even now I'm going to run out of room. So let me start writing these to the side.
Professor, the second one should be 1s also, or 2s?
Thank you, 2s. And then 3D. So just based on my practice, I know we're going to stop at 3D, but you just go as far as you need. There we go. Okay. So there's that order: 1s, 2s, 2p, 3s, 3p, 3s, 3p, 4s, 3d. So notice that the 4s is lower than the 3d. That sometimes confuses people. It just has to do with the internal dynamics of when you have a lot of electrons, the way they interact, the angular momentum, quantum number, the magnetic properties. It's something called spin orbital coupling, and it just results in 4s being lower than 3d. Okay, so it's just something you remember. Again, 28. So you go from lower to higher. 1, 2, 3, 4, 5, 6, 7, right? So you're using Hund's rule there. Within a subshell, degenerate orbitals, you do 1, 1, 1 spin up. Then you go back and do the second one. Okay, so there's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We still have 8 to go. So now this is the first one we've done where we're going to get to the D subshell, right? The 3D. 21, 22, 23, 24, 25, 26, 27, 28. Now we're done. So there's your diagram, a box diagram of the electron configuration. And what I want to point out is that when you end up, see how the last ones are in the D? Here's what happens. When you look at the periodic, I'm going to talk more about this next week. When you talk about the periodic table, so scandium is 21, all the way through zinc, which is 30, okay? These are called the transition metals, right? Okay, they are also, nickel's in there, right? So nickel is 28. Those elements, their outermost subshell is a D. So see how this was 3D? 3D here, we have, this is our highest right here. So if the outermost electrons, meaning the ones highest in energy, are in the D subshell, then it's going to be a transition metal. So you can immediately say, even if you don't know where the electrons are, if you look at the periodic table and you say, oh, that's a transition metal, you know now that the highest orbital that has an electron is going to be a D. Okay. Now, what would happen if we had more? We also have 4p, right? But we don't have enough electrons to get up to 4p. So those are just going to be empty. Those are spaces further from the nucleus that are just empty in this case, because nickel only has 28 electrons. Okay. Now, what I would like to do is to show you a shorthand notation. Because drawing a diagram like this is tedious, all those boxes, and I had to give up the fact that they're actually converging, right? Remember, they're getting closer and closer in energy as you go higher. I was drawing them equally spaced just because it gets hard to draw it like that. So here's the shorthand notation. What you do is you start at the beginning, you start at 1s, and you just write down the orbitals that have electrons. Okay, so I'm just going to start from the beginning and go up. Okay, we're going to stop at 3D, right? Because there are no electrons in the 4p. Then you count up how many are in it. How many are in that subshell? And you write it as a superscript. So you've got 2 electrons here, right? 1, 2. So you put a 2 as a superscript. You got 2 in here. So you put that as a superscript. You got 6 here. So you write that as a superscript. You got 2 in here. So 2, 6, 2, 8, right? There's 8 in there. So you write 8. And so that's a shorthand notation. Again, it's showing you from lower energy to increasing energy, but it's a lot nicer, right? It's a lot simpler. We don't have to draw those box diagrams. You lose a little bit of information with this notation, this shorthand notation. Here's what you lose. 2 unpaired electrons, right? You can't tell that from 3D8. You could maybe memorize, oh yeah, if you've got 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, we're going to have some unpaired electrons, but you don't know how many that easily. So you're kind of giving up looking at it to see that there's 2. So often what chemists will do is they'll say, look, I know all these are going to be paired, so I'll just write out the last one. And then put 8 there. 1, 2, 3, 4, 5, 6, 7, 8. And now they can see there's 2. So that's the way, that's kind of a way around it. But this is a nice notation here because it's a lot simpler than drawing this big picture. Okay. Let me see, are there any, I want to see if they give you any like really hard ones, like not hard, but ones that have a lot of electrons. It looks like they're just giving you the standard transition metals and main group elements and non-metals and stuff like that. So let me just do one more. I'll do let's do, that's nickel, cobalt. I'll do cobalt. Let's do sodium. Sodium's an easy one, but it's good to get practice. Okay. So for this one, I'm going to do, sorry. We're going to do a neutral atom of sodium. And let's do the diagram first. And then let's do the shorthand notation. Okay, we'll do both. Okay, so sodium is element number 11. Okay, so 11 protons. It says it's a neutral atom, so it's got 11 electrons. Okay, so let's do it this way. We'll do 1s, 2s, 2p. So now I'm actually going to draw these connected to each other just to show you that they're at the same energy or whatever. 3s. Now we know we only have 11 electrons, so there's not that many in there. It's not like we have 20 or 30. So I'll stop at 3p. But I'm going to assume we don't go that far. Okay, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11. Okay, there you go. There's your diagram. So how would we write this as a shorthand? You just write the ones that have electrons in them. 1s, 2s, 2p, 3s, and then you write the number that are in that subshell as a superscript. 2, 2, 6. You're going to see those numbers a lot. And then there's only one there. And we would say that there's one unpaired electron. Right? There's only one electron that doesn't have a partner. It's unpaired. So there's one unpaired electron. Okay. The terms you'll see with paired electrons is diamagnetic and paramagnetic. This means fewer unpaired electrons. This means more unpaired electrons. So for example, suppose I said this. Which one of these two is paramagnetic? Which one is diamagnetic? Paramagnetic has more unpaired. So this right here would be paramagnetic. Diamagnetic means fewer unpaired electrons. This one only has one unpaired electron. So this would be diamagnetic. Okay, and there we go. All right. So that is essentially what you got to do in chapter 6. What I'm going to do on Monday is I'm going to go through a couple more and sort of wrap it up, maybe look at a couple more problems, but we've pretty much gone through everything. It's kind of cool. So we're sort of ready for the next chapter, which is 8, but I'll spend a little more time on Tuesday with chapter 6, because this assignment is actually not due until the 23rd, which is, what is that? It's like, today's like the 7th, 6th or 7th. So 6th. So that's actually a couple weeks from now. So I'll spend some more time kind of going over this a bit more because it's all new information for most people. So we'll wrap this up. We'll wrap up chapter 6 on Tuesday. And then on Wednesday, then I'll start getting into chapter 8, which is chemical bonding. Now, based on our time, we seem to be doing pretty well. There's one extra credit topic, which is chapter 9. So I should have time to go over that though. So that'll be helpful. It's extra credit, but I'll have time to go over it. And that's a short chapter. It's only 8 topics. So it's kind of worth your while to spend time on that because 8 topics, you get credit. But chapter 8 is kind of long. So we'll be spending some time on chapter 8 starting next Wednesday. Okay, so there you go. So have a great day. If you're not in touch with me, have a great weekend. But do reach out to me if you have any questions. I should start working on the thermochemistry lab reports to get those into Alex scores over the next couple of days, certainly by the end of the weekend. Okay. So take care, everybody.
Thank you,
Thank you.
Professor.
Bye.
Thank you.